In this video, I'm going to talk about SUVAT as it's related to rotational motion. That means I want to talk about kinematics, or how things move, accelerate, but I want to do it with rotational motion, not in a straight line. So please take a moment and read the success criteria I plan to cover during this video. Okay, so let's start off by talking about the SUVAT. Many people know this by many different names, S being the distance traveled or change position, U being initial velocity, V being final velocity, acceleration, and time. Let me just write those words in. Now, if I want to, instead of talking about a straight line, I'm going to rotate. Now, there is a slight difference between circular motion and rotational motion. So, circular motion is when something's moving in a circle. I give the example of the Earth going around the Sun. And for the Earth, its circular motion takes 365 days to do one complete circle around the Sun. Whereas if I'm talking about rotational motion, now we're talking about 1 day. That's how long it takes for the Earth to rotate on its axis. Now, if I'm talking about the whole piece, I could be using the same kind of idea of circular and rotational. For example, I have a turntable going around and I've got a penny on the edge. If I'm just talking about the penny, it is undergoing circular motion. But if I talk about the whole turntable, now I'm going to be relating the motion to rotational. Just kind of keep that in mind. Now, in rotational motion, I'm not really interested in the distance traveled because I keep going around and around. What I am interested in is the radiance that it goes through, or I could turn that into degrees if I want. So we're talking about the angular change. And instead of velocity, I'm now interested in its angular velocity, sometimes also called angular frequency. And I'm going to use the letter omega with an I for initial. Now let me point out, if this is the angle and that's in radians, then that means my initial angular velocity is going to be in radians per second. And we don't usually write radians a lot when we do things, so this would be a per second, which is also known as a hertz, which is why this is sometimes called an angular frequency. It's not a big deal. Don't let it mess you up. I also have final angular velocity. And for acceleration, we're not going to use an A, we're going to use an alpha. And T is going to be exactly the same. It doesn't matter if I'm going in a rotational motion or in a straight line, time is time. It's a scalar. One of the biggest things that you can do here is remember these translations. In other words, what is it that I've already learned? What is the new letter and the new idea when I talk about rotational motion? If you can already do this, it's just like learning a new language. I'm just going to take all the equations I knew before, and I'm going to change them into these variables that I use for rotational motion. So let me do the translating for you. This would be my change in angle, but for translation, that would have been an S. And final angular velocity, well, that would have been a V if I was in a straight line, plus U over 2 times time. This is one of our kinematic equations that we have in our data booklet for traveling in a straight line. I'm just translating it into rotation. If you look at here, V equals U plus AT. S equals UT plus 1/2 AT squared. We already know these equations. We just need to have some practice translating from linear motion into rotational motion and setting up our questions. Now that we've gone through the theory and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. So let's get into some examples. I have here carousel at an amusement park. I've got 2 horses, and you can see that the white one is farther to the edge and the blue one here is closer inside. It says compare the linear velocity of each child. Now, if I talk about the linear velocity, it's not traveling in a straight line, but if you think about it, I could also call that a tangential velocity. In other words, if this pole here that's holding this horse in place, if it disappeared, how fast is it moving? And we know that without that pole, it's going to travel in a straight line. Also, if I was doing this, I would also be thinking about it moving at a constant speed, so that would be distance over time. Now, if you think about this, the white horse will travel farther distance because it's going to have a larger circumference to go around than the blue horse. That means the white horse's linear velocity or tangential velocity is going to have to be greater than the blue horse. Okay, now in B, it says compare the angular velocity of each child. Well, if I'm going to be thinking of angular velocity, let me translate this into our rotational motion. Instead of V, I would have an omega. Instead of D, I'd need a theta, and times the same. So let's do the same thing. How many radians will this horse go through in the same time that the blue horse goes through it? Well, they're going to have the same number of rotations per second. That means they're going to have the exact same angular velocity. Let's try another kinematics problem. Remember, we just need to make sure we keep translating it. So our carousel is initially at rest. Initial angular velocity is going to be 0. And I always tell my students to write down SUVAT when they're doing these questions. We'll just build it as we go. We know we're going to increase in angular velocity. And it says at 8 seconds. Okay, so I've got some time. It has a rate of 0.060 radians per second squared. That must be my angular acceleration, so that's the alpha letter. I'm putting radians here to remind me that this is angular. And part A says calculate its angular velocity after the 8 seconds. So that will be the final one. So I go to my data booklet. I'm looking for the one that has omega I, time, alpha, and omega f. And it's already in the right order for me. So I'm going to simplify this, make that easier because that's a value of 0. So I'm just going to have my angular acceleration times my time and my final answer being 0.48. And it's going to have units of radian per second. I'm just going to put that number up here so we can use it later. If the horse is 2.5 meters from the center of the carousel, calculate the linear velocity. Now, we've got this equation here. V equals omega r. Now, this is actually found in the equations for 8.2 where we did circular motion. It's the same equation here. So it's relating our linear velocity to our angular velocity. You know, the farther you are from the center, the faster you're going. If I put in my values here, notice this is 0.48 radians per second. I'm going to be multiplying that by 2.5 meters. I'm going to end up getting my answer with units in meters per second. In this case, my handy dandy calculator tells me it's 1.2. Let me put that back up here. And finally, calculate the number of rotations that would be completed in this time. Well, first I'm going to need to find out what theta is. I'd go back here, I would use these values, not the one I calculated, just in case it's wrong. So I need the one that has theta, omega I, t, and alpha. And again, this is 0, so that will make my life easier. Put in my numbers. Now my answer here is going to be 1.92 radians. Now that's important because that's not what it asked. It asked for the number of rotations or the number of revolutions. So if I change my units, I have 2 pi radian in 1 revolution. So since 1 revolution is the same as 2 pi radians, this is like multiplying by 1. Notice I've written them so my radians will cancel out. And this will give me 0.3 revolutions. So the number of rotations that were completed, 0.3 revolutions. I think we need one more example here. we have a rotating blade and it's spinning at 300 RPM, revolutions per minute. It's then turned off and it takes 3.2 seconds to stop. Determine the initial angular velocity in radians per second. So I'm going to use the same method I used before for changing my units. It's 300 revolutions per minute. And the reason I do this is because somebody else has already made me memorize that I've got 1 minute is the same as 60 seconds, because I need to put it in to get rid of my minute and replace it with seconds. I also know that I've got 2 pi radians in 1 revolution. Now, if I pick up my handy-dandy calculator, I'm going to get 31.4 radians per second. And I know I've got that right because I've got the revolutions here canceling, my minutes canceling, leaving me with radians per second. And for part B, calculate the angular acceleration of the fan blades. Okay, so let me go back to my information. I have an initial value we now know is 31.4 radians per second. Okay, and this has to be in radians per second if we want our values to work out here. My time is 3.2 seconds. I also know it stops, so that's my final one. Remember when we use SUVAT, there are always 4 variables in the equation, so you have to know 3, and the other one gets a question mark. So this is 0, and I'm looking for angular acceleration, and I will be able to find an equation that has all of these in it. So in my data booklet, I've got omega f equals omega I plus alpha t. This value is 0 now. I'm going to rearrange that. I'm going to take this omega to the other side, which means it'll be a negative I divided by the t. That was 31.4 over the time, which was 3.2. And my answer will be in, remember, this is radians per second divided by another second. That will be radians per second squared, which is good because we know that's going to be our unit for acceleration. And kind of ironically, it gives us 9.8 radians per second squared. So this part of angular motion really isn't any different than when you've done mechanics and moving in a straight line. We're just going to translate into our variables that we need for rotational motion, find our equations, and put it in just like it was any other kind of acceleration. So please take one more moment and rate the success criteria, and I hope after this video you can say yes to all of these.